let's take a look and see how you're doing here. So obviously we got everything here in words. So the first thing we want to do is make sure we get the right formulas like we were doing naming. So we're doing some potassium carbonate. Potassium is K plus, right? Carbonate CO3 2 minus. So when we put that together, that is K2CO3 would be the proper formula. And it's going to react with nickel 2 chloride. That means my nickel has a +2 charge. My chloride has a -1 charge, which means I should lay up something that looks like that to begin with. Yeah. If you don't have those, the rest of it's going to be pretty difficult. Yeah. So you got to make sure you got the right sort of formulas. By the way, if you don't recognize it as a double displacement reaction, you should, because again, this is basically two ionic compounds, which basically will switch partners. So the potassium here will end up with the chloride. The nickel will end up with the carbonate. Once again, this is what I was talking about earlier. You do not want to try to write the formula and balance at the same time. You just want to lay up the correct formulas on the right-hand side. And that would be, in this case, once again, K plus and Cl minus, which gives me KCl. Not K2Cl2. That does not exist. Yes. So again, do not try to balance it and write the formula as well. That means also my nickel with a +2 is going to go hook up with my carbonate with a -2 and give me the proper formula of NiCO3. So I didn't care about balancing here. I just wanted to get the right formulas down. Now that I have the right formulas down, we could actually go back and balance it using our coefficients. Again, it is never a great idea to try to do that at the same time, because you will probably end up with the wrong answer. So now that we want to balance it here, perhaps I need a 2 right about there. And I think that's all I need. Yeah, so I think I just need a 2 right there to balance it. We also want to use our solubility rules that we talked about to lay us up some states here. So looking at the first one here, I see potassium, and that's group 1, which means I don't need to go any further. I know that is aqueous. I have nickel, which is a transition metal, but I do have chloride. And remember that chloride is soluble in everything except for silver, lead, and mercury, which is not the case here. So that means that this guy would also be aqueous. In addition, they said aqueous in the words, right? So that tells me it's aqueous as well. When I come to the other side, I see potassium, which once again is as far as I need to go because it is soluble in everything. So I could lay up an aqueous symbol, feel good about it. I could also look at chloride, which again is only silver, lead, and mercury the exception, which is not the exception in this case. So they both tell you the same thing. Coming here to nickel and carbonate, I would want to look at carbonate on my solubility rules, and perhaps you would find that that actually is our solid. Plus, there's nothing else to be our solid at this point. Common sense would tell us it's got to be that one, since they said it's a precipitation reaction, which means something should precipitate, right? Any questions on solubility, how I put it together? Yeah. It balances because if we did like a little table, we got our K, our carbon, and our oxygen here. And before we had 2 potassium on the left, 1 on the right. We had NaCl. We also had 1 carbon on the left and 1 on the right. We had 3 oxygens on the left, 3 on the right. And chlorines, we had 2 and only 1. So I started with potassium to get me a 2. That also fixed the chloride that was in trouble there as well. So that's why we went there. Other questions? This is also one where you did have a polyatomic ion, but it's basically 1 on both sides. So you would want to maybe just go with the traditional sort of balancing. Other questions on that? All right. So now that I have my balanced molecular equation, which is what I'm laid up right there. I could then go to our total ionic equation. So if I were to do the total ionic equation below this, we're going to break apart anything that's a strong electrolyte, which again is pretty much any ionic compound. That is obviously not a weak electrolyte. And anything that is, again, a solid, a liquid, or a gas, and a weak electrolyte, we do not break apart. So in this case, the potassium carbonate would break apart. The 2 would come to the front because there's 2 potassium ions and 1 carbonate ion, like how we put it together, basically. The nickel 2 chloride would also break apart. We have a nickel with a +2 charge. Once again, we do need to include the charges here. The 2 for the chloride would come to the front here to tell us that we have 2 of the chloride ions floating around. On the other side here, the 2 will get distributed to everybody behind. So that would be 2 potassium ions and 2 chloride ions as well. And once again here, since this is our solid, it will stay together and not break apart. In this case, this once again is our balanced total ionic equation. Any questions on that one there? At this point, this is really where we want to look for our spectator ions. So we're looking for ions that are exactly the same on both sides. So looking at this, once again here, I got 2 potassiums on the left. I got 2 potassiums on the right. I also have 2 chlorides on the left, and I have 2 chlorides on the right. Once again, these would be our spectator ions there. Once again, we do just cross those guys out in our total ionic equation, and that is going to leave us our net ionic equation, which once again is pretty much what is happening in this reaction. And that is that the nickel ion is going to find the carbonate ion, and they're going to come together to form our solid, which once again, as we talked about, is really the driving force for why a chemical reaction takes place. Is the formation of a solid is one of the reasons. And this is really what happens when you dump both of those together. It is those 2 ions coming and finding each other and being attracted to each other that they basically go and drop out of solution. Any questions on that there? Once again, if you balance the original molecular equation correctly, when you get to your spectator ions, they should completely cancel out. So if you get to that total ionic step and your spectator ions do not completely cancel out, because you got different amounts on each side, it probably means you balance the equation wrong. So that's a good way to sort of check yourself. They really should kind of completely cancel out. Any questions on any of those steps there? All right, let's try a couple more here that we got in your notes then. All right, so for each of these, let's do all 3 again. Good practice. Let's do the molecular equation. Let's do the total ionic equation, or the tie, if you will. And let's do the net ionic equation, the nye. Okay, let's take a look here. I guess I must have saw this one before, because that's right, the example I did earlier today. So you should have a pretty good idea. It's the first one here. This again is a double displacement reaction. That's positive, negative, which means again, these guys are going to switch partners. Thank you. So we want to get the right formulas on the right-hand side. So potassium is +1, nitrate is -1, which gives us KNO3 as our proper formula. And silver is +1, and chloride is -1, which means we do get silver chloride. Using our solubility rules, already done on the left-hand side, we see potassium. That is all we need. So that's going to be aqueous. We see chloride, and this is, again, one of the exceptions for chloride. So instead of being soluble, it is going to be the opposite, which means it is going to be insoluble. And this would be a precipitation reaction as we did form a solid. In this case, we would want to balance it up. So taking a look at the balancing aspect, I believe we are balanced. Yeah, we got the same numbers on each side. 1 potassium on each side, 1 nitrate, 1 chloride, and 1 silver. So this would be our molecular equation. To go to the total ionic, we're going to break it apart. We would have K plus and Cl minus. The next guy would also break apart, silver plus and nitrate. Our potassium nitrate will break apart. Potassium and nitrate. And once again here, the silver chloride, which is a solid, would stay together. And this would be our total ionic equation. Any questions on that there? Our spectator ions, looking at our total ionic equation, is going to be our potassium on both sides and our nitrate there on both sides. Those are going to be our spectator ions, which we will cancel out, leaving us the silver ion is going to find the chloride, and that is going to form basically a white precipitate, which is known as silver chloride, and that would be our net ionic equation. Any questions on any of those three there? All right, looking at the second one, also double displacement reaction. We do see this is a positive, negative guy, positive, negative. So once again here, we're going to start by starting with the right formulas on the right-hand side. That means the sodium will cook up with the chloride. Once again, sodium is only +1, chloride is -1, which gives you NaCl, not Na2Cl2. I say that because people write that all the time. Calcium here is +2. Sulfide is group 6, which means it's -2. That gives us CaS as our proper formula. Now that I do have the proper formulas, I can balance it. And in this case, I do need to put a number. And once again, I think I just need to put a 2 there in front of the sodium. And that should balance everybody up. 2 sodiums, 1 sulfur, 1 calcium, and 2 chlorides. Using our solubility rules here, sodium chloride is soluble or insoluble? It is soluble. Yeah, as soon as we see the sodium. How about calcium sulfide? Is that what it is? Yeah, calcium sulfide. Calcium sulfide is soluble as well in this case. Yeah, so they are both soluble. So that would be our molecular equation. And if we went to our total ionic equation, we would get this: 2 sodium ions plus a sulfide. The calcium chloride would break apart into a calcium ion and 2 chloride ions. The sodium chloride would also break apart into 2 sodium ions and 2 chloride ions. And the calcium sulfide, because it's aqueous, would also break apart into a calcium ion and a sulfide ion. Yeah. Which means when I go to find my spectator ions, I got 2 sodiums on the left, 2 on the right. Sulfide left, sulfide right, calcium left, calcium right, 2 chlorides, 2 chlorides. Everything cancels out, yeah? Which means for the most part, you have no reaction, yeah? So really, because everything is aqueous, there really was no reaction that took place. Basically, everybody is still floating around happy in the solution. Remember, really, for a reaction to take place, you need to make a solid, which did not happen in this case. You need to make water, which did not happen. And there's no electrons being transferred here. So there was really no reaction that actually took place in this case. So if you come across a situation where all you make on the right-hand side is aqueous, it's really no reactions, which you should write there, because there's really nothing happening in this case. Yeah. It is an exception, I believe, right? So calcium is one of the exceptions. So because it's an exception, it's basically the opposite. So if it's normally insoluble, then it would become soluble if it's an exception. It would be. So basically what you have here is just calcium ions still floating around, and you have sulfide ions still floating around. They're really not going to come together, even though we write them together here in terms of a formula. Because they're aqueous, that really means they're just apart, basically floating around in the solution. Other questions on that? All right, I feel the professionality happening here. So one last one. This one, just write the molecular equation. So just do the molecular equation in this case. The balanced molecular equation. Good practice, I suppose, for Thursday as well. least the nomenclature part, I suppose. Yes, sir. It is not, but the naming part and writing formulas will be. So that part is practice, I guess. Just your test. I'm just kidding. Just special tests around the room. There's other be. I'm just gonna put exam 3 to some people and give some people exam 2, and some lucky people exam 4. No, there actually is an exam 4. I know it's sad. I know. It happens like right before the final. I give it to you exam 4, and then you take the final when you turn it in. Bring a sleeping bag that day. We're just gonna be here for a while. Get comfortable. You don't need to sleep. Well, it might make you feel more comfortable as you're taking all those exams. The comfort of zipping yourself in the sleeping bag as you're taking the exams. It gets cold in here sometimes. They put the air on. You might want to have some warmth. That's what I'm saying. I know the other day when we were using the big ones, when we were doing the evaporation, it got really warm in here. It's like, all right, so let's take a look at this one. So we're just writing the molecular equation in this case. So we want to put it all together correctly. You should identify this as a double displacement reaction, positive, negative, positive, and negative. So once again, when it goes to the other side, the positive guys are going to switch partners. We once again want to make sure that we use the correct formulas first. So NH4 is NH4 plus, and that's going to be hooked up with acetate there. That's this guy, which is -1, which means we do end up with NH4 C2H3O2. We are then going to take lead, which in this case, lead is carrying a +2 charge. I know that because acetate's -1, and there's 2 of them there. The sulfate here is also a -2 charge because that's what sulfate is, and that gives me PbSO4 in this case. Any questions on that part? Now, once again, that I do have my sort of formulas correct here, we're going to balance it. We got a lot of polyatomic ions, so might as well start that way. We got 2 ammoniums, and I can put a 2 there. That also gives me 2 for the acetate, which is what I need. And now I am balanced. At this point, we could also do some states here based on our solubility rules. So once I see ammonium, that is soluble in everything. So that's as far as I need to look. I see acetate, which is also soluble in everything. So that's as far as I need to look. Once again, I see ammonium over here, so I don't need to look any further. And what about lead 2 sulfate? That is going to be a solid, right? So that is going to be our solid here, and that would be our balanced molecular equation. By the way, if I just wanted to leapfrog to the net ionic equation, I know that my solid would be there, right? And I know that that solid is a lead 2 ion and a sulfate ion. And I could actually just work backwards if I wanted to from the solid and break it back apart and get our net ionic equation really quickly as well. That would mean, just quickly looking at it, it is the ammonium and it is the acetate that are our spectator ions in this case. Yeah. Any questions on that? So you can actually kind of work backwards from the net ionic equation if that's all you need to write. And it would always be obviously the solid on this side, the liquid, those guys would be pretty much on that side, and you can break it back apart. Any questions on how to write those 3 equations, which obviously is what the study assignment's about? Any questions? Okay, so as you finish up with a couple more slides here about double displacement reactions, which you might come across in that study assignment. So the next type of double displacement one is really an acid-base reaction, and it's sometimes referred to as a acid-base neutralization reaction. And basically, this meets the criteria of making water. So the precipitation reaction, which is a double displacement reaction, makes a precipitate. And this guy here basically will make water, and it's a double displacement reaction. An acid is basically anything that could form a proton or an H+ ion. sometimes referred to as a proton, are the hydrogen ion. Hydrogen ion. Hydro spelling does count, I guess. Ion. Yeah. Also, H3O plus is also the same thing. So in acid-base chemistry, if you ever see H plus, which is the hydrogen ion, is the same thing as H3O plus, which is the hydronium ion. It's basically the acid part of the solution. The overall reaction when you take an acid, especially a strong acid and a strong base, no matter what combination of strong acid or strong base that you do, you will always produce a salt and water. A salt is an ionic compound. And ultimately, what is happening is the acid is giving the H plus, the strong base is giving the OH minus, and the net ionic equation for every strong acid, strong base combination is basically, this is what is happening. You're basically forming water. So let me write it a little bit higher there. So you're basically forming H plus, OH minus coming together to make water. So ultimately, that is what's happening in an acid-base reaction. And once again, that comes from the acid, that comes from the base, and that water is being formed as a result of it. So acid-base reactions are really double displacement reactions, and it's sort of a subcategory of double displacement reactions where basically it is still a double displacement that is happening in this case. Here are some strong acids and some weak acids, which will be helpful as well as you go through that study assignment. You will come across some weak acids, and in a weak acid situation, for example, when we get to, let's say we had, speaking of net ionic equations and all those things, let's say that we had a weak acid like HF that reacted with sodium hydroxide. In this case, it is a double displacement reaction, positive, negative. Once again, the H and the OH are going to come together to make water as they switch partners. And the sodium and the fluoride will come together to make an ionic compound. Now, if you take the molecular equation, which is this guy here, and you did the total ionic equation, because this is a weak acid and a weak electrolyte, you would not break it apart. It would still stay together when you get to the total ionic. You would then break apart the sodium hydroxide, which is a strong base and a strong electrolyte. You will keep together the water, which is a liquid. So again, the liquid, gas, or solid will not break apart. And the sodium fluoride here will also break apart. So it is a little bit different when you have a weak acid or a weak base involved. When you get to the total ionic equation, you're going to keep it together. It will also affect, in this case, the spectator ions. What is our spectator ion here? It is just the sodium. We actually only have one in this case, and that is the only thing that will cancel out. And that will leave us for our net ionic equation, something that looks a little bit different. Well, we will have HF, which is still together, and the hydroxide will come together to make the water and the fluoride. So you will run across some, I think in that study assignment, where you'll have some weak acids. So it is treated a little bit different as you go through the different steps. You basically keep them together, and it will still be there at the end in a sort of combined form. Any questions on that? So again, because that's a weak acid, a weak electrolyte, you do keep it together. So anytime in that total ionic, weak electrolyte, solid, liquid, or gas stays together, you don't break it apart. Any questions on that there? So getting back to that table there, this could be helpful to reference. So here again are some of those weak acids I think I might have wrote on the paper earlier. There's some of our strong acids, which again are strong electrolytes. So if it's a strong acid, strong electrolyte going to break apart. If it's a weak acid, weak electrolyte going to stay together. And same thing with here are some bases. Most strong bases will be group 1 and group 2. heading from like sodium, potassium, make a right to calcium and down to strontium and barium. They typically are going to be your stronger bases. Here's some examples of some weak bases. So again, if you came across any of those weak bases, you would also keep it together when you get to the total ionic equation. So as I mentioned before, acid-base reaction always produces a salt and water, and it is always the H from the acid, the OH from the base, making our water. And then obviously our salt would be this guy. Once again, if we ran through this, this would be H plus and Cl minus. The sodium hydroxide would also break apart into Na plus and OH minus. The sodium chloride would break apart into Na plus and Cl minus. And once again, here our water would stay together. This would give us our sodium on both sides, which are spectator ions, and not our hydroxide, but our chloride on both sides are spectator ions here. Back here. Put my guy on the wrong side there. Try that. There we go. And our chloride would cancel out. And once again, giving us the always net ionic equation here, the formation of water when we take an acid and a base together. It is pretty much always the reaction that takes place. Like I said, any combination of strong acid, strong base, that is pretty much where you're going to end up with in terms of the net ionic equation. And again, it is the sort of second reason why a reaction takes place, that formation of water. Any questions on that there? Okay. All right. So lastly here, I think we're going to look at some double displacement reactions that actually will form gases. So there are certain double displacement reactions that will form gases as a direct result of the double displacement reaction, or as sort of indirectly. So what will happen is some product will continue to react and really decompose into a gas. So an example here, if we take potassium sulfide, but some sulfuric acid, it is a double displacement reaction here. And directly off of the double displacement, the H plus and the S come together and will directly produce this gas, which is hydrogen sulfide gas, which you don't ever want to smell because you will know if it's in the room. It smells really bad. So we will produce hydrogen sulfide gas as a direct one. Now, on the second one, it is a double displacement reaction that takes place. And once again, we form K2SO4 and H2SO3. What happens in this case is this product will then go through what is known as a decomposition reaction. So it will very quickly break apart into H2O and SO2 gas in this case. So this is an example of a double displacement reaction that actually forms a gas as a secondary sort of reaction occurs, not directly, but one of the ones come apart. Very commonly, anything that involves carbonate, this occurs with an acid, like HCl and sodium carbonate. We'll make some carbonic acid plus some sodium chloride. This carbonic acid will very quickly break apart into H2O and CO2 gas. So very quickly decompose into carbon dioxide, plop, plop, fizz, fizz, Alka-Seltzer, all that kind of stuff. Kind of the same idea. It'll start fizzing, maybe a little bit like that as well. So another sort of outcome of a double displacement reaction is actually not forming necessarily water or a solid, but you could actually form a gas. And obviously, if you had a gas that would be formed, it would not be broken apart either, as it would be covalently bonded together. Here's a table that kind of walks you through the different combinations that you could get and the gases. Most of them, as you can see here, are sort of a result of a decomposition reaction happening. So if you have carbonate or hydrogen carbonate, you're going to get CO2 gases going to form. If you have basically sulfite or hydrogen sulfite, you'll get some SO2 gas form if you react it with an acid. And if you have ammonium, NH4 plus, and you react it with a base, you will actually get ammonia back, NH3 gas. The direct one is you have anything with sulfur or hydrogen sulfide, you will get basically hydrosulfuric hydrogen sulfide gas being produced directly. So it's a good little table to reference. Again, occasionally you may produce some gases. Usually involves, as you can see here on the left, something with carbonate, something with sulfite. They're very common that will sort of produce gases as a result of it. Any questions on that there? All right. That wraps up the double displacement banner of reactions. Again, underneath there is our precipitation reactions, which forms a solid, our acid-base reactions, which forms water, and secondary to that, again, is the formation of a gas. Any questions on any of that stuff there? All right, we will wrap it up then for our lecturing part here.